All right, thanks for having me here today. So we're going to talk about how to bridge reinforcement learning with simulation software. And of course, if you're a reinforcement learning practitioner, you might ask, all right, aren't all reinforcement learning experiments basically based on simulations? And in a way, that's true, but it's still not the full picture and not that easy, since it misses the point that there is established enterprise simulation software that you're probably unaware of and which can be leveraged to do really cool reinforcement learning projects. And that is a great opportunity as well. All right. Okay, so before we dive into any specific software, let's talk about a concrete problem that we have right now. So let's say you have a car company or you produce lightsabers or something else, doesn't really matter. As long as you have a large enough factory grid with production steps that your product parts have to go through. And as long as you have that, we're good for this example. But let's just assume we have cars that we manufacture. So one question that you might have is, how do I move objects in my factory efficiently from A to B? So for instance, in the picture to the right, how does the car at point 19 up here, the red one, get to 4B, right? So of course I have to tell you the rules, otherwise it's no fun, right? So it goes as follows. The cars marked with a C move through the factory on tables marked with T, right? The cars need to be delivered to one or several nodes on the factory grid to complete a production step, right? Once all production steps are done, the car is ready, okay? And of course, the tables can't move arbitrarily, but they have to move along the grid, right? Those are the orange lines you see here. And the problem is, of course, that tables can't directly pass each other just like that. They need to move out of the way first, right? And of course, the whole problem becomes more and more complicated the more tables you have on the board, right? So it's a bit like a 15 puzzle on steroids, right? Which might explain the picture on the left, right? So you have to move tables out of the way to get other tables to certain positions, okay? Also, we have some more specific rules to the problem at hand, but they aren't really that interesting for that talk, so I'm just going to skip that. Just take it that it's kind of a complicated problem that's closely related to the 15 puzzle you probably know. So for instance, in this particular setup, how would you solve this problem getting the car from point 19 to 4B? So we have this table at 1C here, so that has to move out of the way first. For instance, by going to 1B, 1A, 16B, 16A, 15B. Then it's out of the way, so the car at 19 can itself move to 1C, 1B, 1A, 16B, 16A, 17A, 17B, 3B, 3A, 4A, 4B. Done, right? And so that's the best solution you can get in this particular scenario. But of course, it's unimaginable that if you have many more tables on the board, this problem becomes quite complicated. And also, given the size of the factory and all those restrictions in place, it's clear that it would be very difficult to put a purely rule-based system in place here, right? In fact, if you know a bit about it, this whole problem and the setup screams reinforcement learning, right? So, but how do we apply it, right? So this is just a picture. Okay. So here's the problem, if you will. This is an actual problem from an actual existing customer. And while it would be nice to start completely from scratch, we really can't, right? And it might not be advisable, right? And this is the standard scenario for any company of that size, right? If you're a big manufacturer, you don't come in with a clean slate. You have software that simulates your processes, right? And even if you could do everything from scratch, that would be something you would have to do first, which is costly, right? The implementation cost is there. Specifically, in this case, the problem was already modeled with a piece of software called AnyLogic, right? Which also has a cloud version. And so this is just a random picture that is not related to the actual problem, but it could look like this, right? So, and the fact that this problem, this factory puzzle I presented to you, has been modeled with AnyLogic is a good thing, because it's a very rich and complex tool that takes away a lot of pain points, right? So things that you would have to implement on your own otherwise. For instance, you can easily model objects using a user interface and dragging and dropping predefined objects that are already there for you. You have the grid you don't have to define, and the nodes are there, and you can connect them. So it's quite easy to work with it. And AnyLogic on top of that can also handle complex state transitions and handles events for you, synchronicity, and so on. It also comes with tooling to visually simulate what's going on your project, and that's particularly useful for communication, right? If you want to show your manager what's going on, or what you've been implementing, and maybe you have a heuristic that works and you want to show that off. So that's easy to do if you start with a simulation in AnyLogic, right? So, and it's so convenient once you're used to it that it's hard to let go of because of all the features it has, really. So from a reinforcement learning perspective, you should think of AnyLogic as a way to build, highly complex environments. And by that I mean environments in the reinforcement learning sense, state spaces, if you will, but without any direct access to any of the tools you would like to use. Okay, so AnyLogic speaks Java natively, so it's not quite clear what to do to apply your reinforcement learning stack, which is most likely written in Python, right? So what do you do? All right. So if we flip the problem on its head and start with the toolbox you want to use, namely the full Python arsenal, maybe using RLlib, or maybe OpenAI baselines, or Keras RL, certainly OpenAI Gym would come to mind, or something else, you name it, right? How do we get to the same implementation? I mean, now we have the complete reinforcement learning toolbox, but we lost our simulation implementation. And the answer is, it's not that easy. You could use something like maybe SymPy or Celebim, which are Python tools for simulation modeling, but it's really no match to something production ready like AnyLogic. And also your customer most likely will not be very happy with that. They want you to use their exact model, and only if only to ensure correctness of the model, which is quite a big one, right? Yeah, so that doesn't really work. Okay, and on a side note, you should see all of this as an opportunity as well, because if you've done RL for a while, you're probably tired of I don't know, toy examples like card polls or Atari games, right? Sure, you can hope that yet another large AI research lab open sources their next few environments. But really, in practice, if you ask yourself, where do the simulations come from that we hope to crack, that we hope to crack with deep reinforcement learning, right? And if you have such simulations, how do you make use of them, right? So those are interesting questions. And so having said that, it totally makes sense to connect both worlds, right? So how would you do that? And one possible answer is use Pathmind. And so I'm going to explain a bit what Pathmind as a company is by walking you through its main product, right? So first, if you have an existing model, like the factory puzzle we talked about, implemented in AnyLogic, you can add a plugin called Pathmind Helper. And you see Pathmind Helper here on the left of the screen, right? And that's the first step. And if you look at this closely, you will see familiar patterns there, right? So for instance, you can define observations and reward variables, actions, and done conditions. So this is something, if you use reinforcement learning regularly, you would recognize the terms, of course, but it's presented in a way such that AnyLogic users can actually utilize that and provide information that they can understand. All right. So this Pathmind helper is essentially the glue between your model and the reinforcement learning world. And this shouldn't be underestimated, because it's really difficult, as it bridges two ecosystems that don't have much in common at all, right? Okay, and once you have that, if you have all of that defined for your specific problem, what you then do is the next step to export the model as a standalone application. So that would be a jar, right? And upload it to the Pathmind web application. And internally, what Pathmind will do is it will create an RL environment from your specifications and use Ray and RLlib to run experiments internally, right? And in the third step, you can run as many experiments in the web application as you'd like by altering the reward function and other aspects of it as well as you see fit, right? And then once you're happy with the results and all the reward curves are as you want them to be, you can re-export, if you will, the resulting policy and plug it back into your AnyLogic model. And from there, you can use all the niceties that AnyLogic comes with. For instance, run Monte Carlo simulations against baseline that you have previously defined, and so on and so on, right? Awesome. So, okay, having said that, so this is like the very high level overview of what Pathmind does and what its capabilities are. But what does that in concrete terms mean for the factory problem that we set out to solve, right? So leveraging the existing model, you first need to define observations and actions, right? And all right, so we also need to specify what the actors are, right? And there's one particular candidate that is quite obvious, namely the tables can move on the factory grid, right? So we should just make the tables our agents. And tables can move in 4 basic directions, so up, down, left, and right. But they can also just stand still, which might be beneficial, right? So after all, we have five actions in total, right? And observations, I can't really tell you how we did that or how we currently do it, but they certainly need to entail all of the cars, right? All the tables they sit on, and where those cars need to go, respectively, right? So, and as I indicated before, this puzzle is done when all the cars have gone through all of their production phases, meaning everything has been delivered, right? And that's, so what I just said naturally translates into a done condition for reinforcement learning, right? So then all that's left from that side is, and that's often the case, shaping the reward function. That is quite intricate and complicated. But the basic idea here is to award each delivered car with a fairly high reward at the end and punish things such as illegal moves and collisions along the way, right? Okay, so this is just the setup, observations, actions, rewards, and so on. Internally, what we do right now is we set up a RLlib multi-agent env. So in which each table in the factory represents an agent, right? And the agents are homogeneous enough because all tables basically behave alike, right? So we just use one shared policy internally. And we're currently using proximal policy optimization to tackle this problem, together with a population-based training scheduler from Ray, okay? And one technique that helps immensely with this situation and this problem is to simply forbid illegal actions by masking them, right? So there's a technique called action masking in RLlib that we use quite heavily to tackle this problem. And so this way, agents don't have to learn to navigate the heavily restricted grid first and can focus, so to speak, on achieving their goals quicker, right? Okay. Awesome. Okay, now that we've talked about the problem for a bit, let's see how all of this could look like in practice. So I brought you 2 videos, both working with 8 tables, 3 cars, and those 3 cars have 2 production steps each, respectively, right? So the first video is completely random, right? So this is where we start out, so to speak, and you will. All right. So you see that tables and cars move, and but nothing really happens, right? So for some reason, I don't know why the cars are suddenly blue, but they were red before. But that doesn't really matter. But the point is, you see behavior here, but it doesn't lead to anything at all, right? If we check out the other video, you will see that the cores move and the tables move out of the way until all of the cars have been delivered, right? So you will see that one after another, the blue guys will disappear and the tables that lie beneath them will surface, right? And after the full simulation is finished, it will stop, right? All right. So the first one is done, last one is done, right? So in the end, it's a bit quick, but I think you see the point, right? All right. All right. You should also note, however, that this is work in progress, right? The current solution, if you look closely, works on production phases sequentially, and often leaves a lot of tables idle. What we want is a simultaneous solver if possible. So there is still room for improvement, but we're slowly getting there with this problem, right? Okay, and to wrap up this whole factory puzzle problem here, I just wanted to mention that we should not forget here that ultimately the goal is to bring this solution back to the actual factory, right? But that's completely for another day, right? Okay, so in conclusion, you see how Pathmind solves an interesting problem that not only opens up the world of reinforcement learning to established simulation software, it can also bring some exciting new problems to RL practitioners that they currently don't have access to. And solving those problems solves actual business needs, which is cool, right? So if you want to learn more about Pathmind, check out their website at pathmind.com. And even better, if you want to get your hands dirty with some actual examples and work through them, follow the link below on the slides here, and I'll share them after the talk, right? So if you're interested in my personal work, check out my GitHub or follow me on Twitter. Okay, thank you.